Over the last few videos, we built up the rules a fluid has to follow, how it moves, and the fact that mass can't simply appear or vanish. But the equations on their own aren't a solver. So how does a computer actually find the velocity and the pressure everywhere in the flow? The velocity, we can march forward in time. The pressure is the part that's harder to pin down, and one repeating loop is what ties the two together. How a solver finds the pressure using the simple algorithm. Here's the plan. First, we tidy the equation. Then we see why the pressure is the hard part to find. Then we guess a pressure and fix it from the leftover mass. Guess, check, correct, repeat. That loop is called simple. In earlier videos, we built the full law of motion. Density times acceleration equals the pressure force, friction, and gravity. For most flows, we simplify it. First, assume the fluid is incompressible, so its density stays constant. Divide everything by density. Friction turns into the kinematic viscosity, nu, and gravity is just a constant background push. We absorb it into the pressure and set it aside. What's left is the form we'll actually solve. In finite volume, the flow lives on a grid of little boxes, called cells. Across each face of a cell, fluid crosses. Let UF be how fast the fluid crosses a face, and AF the area of that face. Multiply them, and you get the volume of fluid passing through that face every second. Mass conservation for one cell is then simple. Add up UF times AF over all the faces, and it has to come to zero. Whatever volume flows in must flow back out. Let's discretize the momentum equation on a face one step at a time. Take one velocity component and write its convection as a flux. Now do exactly what the discretization video did. Integrate over the cell and use the divergence theorem. Every term becomes a sum of fluxes through the cell's faces. Convection becomes the mass flux through each face, carrying velocity across. Friction becomes a diffusion term set by the velocity difference, and pressure becomes a difference across the cell. Finally, group every term by the velocity it multiplies. The center velocity collects one coefficient, each neighbor collects its own. That's the discrete momentum balance for the face. Now just divide it by the central coefficient, and there it is. HF is the sum of each neighbor's coefficient times its velocity divided by the central one, the neighbor weighted average, and D is the face area over that same coefficient. So the face velocity is HF minus D times the pressure difference. HF is built from the neighbors. The pressures are what we still don't know. Step 1. We don't know the pressure, so we simply guess it. Call the guess P star. Put that guess into the momentum equation, and it hands back a velocity through each face. Because it came from a guessed pressure, we call it U star. Step 2. For each cell, add up the fluxes of U star through its faces. Call the leftover B the cell's mass imbalance. If B is 0, that cell is balanced. But usually it isn't. B is not 0 means mass is piling up or draining out. Our guessed pressure was wrong. We have to fix it. Step 3. Split each unknown into the guess, plus a correction. Velocity gets a nudge U prime, pressure gets a nudge P prime. Subtract the momentum equations, and the velocity nudge ties directly to the pressure nudge. Dropping the neighbor coupling here is the one approximation, and it's why we'll have to repeat. Now demand that the corrected fluxes balance in the cell. Substitute the nudge in, and out comes one equation per cell for the pressure correction. It ties the pressure correction in a cell to its neighbors, driven by that cell's mass imbalance. A Poisson-type equation, and we already know how to solve one. Sweep the grid. Step 4. Correct. Add the pressure nudge to the guess, and nudge every face velocity by the same pressure correction. By construction, the corrected velocity now balances the mass in every cell. Because of that one approximation, a single pass isn't exact. So we repeat the whole loop, guess, solve momentum, check the imbalance, solve the pressure correction, correct. Each pass, the total mass imbalance shrinks. When it reaches 0, the velocity and pressure finally agree. The flow is solved. That loop is simple. Here's the whole thing. On a real problem, flow squeezing through a narrowed tube, a stenosis. The grid is where the equations live. Guess, solve, check, correct, over and over. Watch the flow squeeze through the throat and speed up because the same mass has to fit through a smaller gap. And watch the residual, the total mass imbalance, fall towards zero. When it does, every cell conserves mass, a steady jet through the stenosis. That loop is simple, computing a flow. The loop we built is the heart of it. Real solvers add a few things for robustness. Under relaxation, apply only a fraction of each correction or it overshoots and diverges. Staggered grids, or Ria-Chow interpolation, to stop a checkerboard pressure pattern, and variants like Simplex and Piso that refine the correction. But the same guess, check, correct loop is what runs inside OpenFOAM and Fluent. So, pressure has no equation of its own. We guess it, solve momentum, and check the mass imbalance. That imbalance gives a pressure correction equation. We correct and repeat until the imbalance is zero. That loop is simple, how a finite volume solver finds the pressure. That's all for this video.